we are into chapter 4 now. This is going to deal a lot with graphing things. So we're going to talk a lot in this chapter about like highs and lows and graph maximums and minimums, and that's where we're starting today. Some of this we've kind of really used before. The idea of maximizing and minimizing has a lot of different applications. We're not focusing on the applications right now, we're just finding them. But just kind of give you an idea like why this is important. You know, optimization, you might have to find the shape of a can to minimize manufacturing costs. Or you want the maximum acceleration of a space shuttle. Or the radius of a contracted windpipe that expels air most rapidly during a cough. Or what angle blood vessels should branch so to minimize energy expended by the heart in pumping blood. So there's a lot of different applications, which is part of why calculus is required for so many different majors. You can do it in science, business, lots of different areas. The big thing, what we're focusing on today, are absolute and local maximums and minimums. And we've kind of touched on these before. So the absolute is basically the highest or lowest on the entire graph. They can be endpoints. We talked about absolute maxes and mins back in college algebra even, so we've kind of seen it before. These could also be called global maxes and mins, just kind of depending on the textbook, so either term means the same thing. It's the highest or lowest point on the entire graph when you're looking at it. There's different ways to write it. We can write it as like an ordered pair, or we could say like f of 3 equals 2, so when the f of 3 equals 5, so when the x is 3, the y value is 5. When the x is 6, the y value is 2 is the absolute min. You could say the absolute max is 5 and it happens when x is 3. The absolute minimum value is 2. It happens when the x is 6. So the max and min itself is really the y value, but we use the x to identify where it happens. Those are also some, when I'm talking about maxes and mins, those are called extreme values. So I might just say find all the extreme values. That means find all the maximums and minimums on a graph. In the flip side, local maxes and mins, these are just higher or lower than surrounding points. It doesn't have to be the entire graph, just around the points around it. These cannot be endpoints. Because if it's an endpoint, it doesn't have surrounding points on both sides. So that idea doesn't work. So on this graph, we have a lot of different high and low points on it. This first point, is it a max or a min? It's a minimum. Is it the lowest on the entire graph? Yes. Can it be a local minimum? No, because it's an endpoint. So this is just an absolute min. Okay, when x is b, what would this point be? It's not the highest on the entire graph, but it's higher than the points on either side, so it's a local max. What would this one be? What about this one? It's highest on the entire graph. Would it also meet the criteria to be a local max? Yes, so it is both the absolute and a local. What about this one? Local min, it's not the lowest on the entire graph, but lower than surrounding. Can this one be anything? No, it can't be a local anything because it's an endpoint. It's not the highest on the entire graph, so it's not an absolute. So that's all we have. Alright. Is that okay with everyone? Alright, so let's think about x squared. What does the graph of x squared look like? It's a parabola, 0 squared is 0, 1 squared is 1, negative 1, 1. You kind of have an idea what it looks like. Okay, any maximums and minimums? It keeps going forever, so do we have any maximums at all? No. So, the point 0, 0, and you can write it as an order pair, you can say f of 0 equals 0. What would that point be? It's a minimum. Is it local or absolute? Both. It's lower than surrounding points, and it's the lowest on the entire graph. So it is both. And this one has no maxes. Alright, you guys take a second. Think about x cubed. So think about what that graph looks like and your maxes and mins. Fair. If you don't know, 0 cubed is 0. 1 cubed is 1. If you wanted, you could do 2 cubed is 8. Negative 1 cubed is negative 1. So negative 2 cubed, negative 8. If you need to, if you don't know what the graph looks like, or you don't remember, you can always plug in points. Does that have any absolute maxes or mins? No, we have arrows going forever in both directions. A local max or min, is there like a peak or a valley here? No, this one has no maxes or mins. 0, 0 is the only place where it kind of flattens out, but it's not higher than the points on both sides or lower than the points on both sides. So this one has none. Let's look at this one. And I apologize. I was trying to be lazy and copy a picture out of take a screenshot of a picture of both instead of creating my own, so it's a little hard to see. So this is an open circle right here. This is an open circle. So this is my graph. Absolute max. Is there a point that is the highest on the entire graph? Yes, what is it? 4, 3. F of 4 equals 3, or you could write it as an order pair, doesn't matter. Absolute min. Is there a point that is the lowest on the entire graph? We look right here. This is the lowest on my graph, right? But what's wrong with it? It's an open circle. Can you tell me the closest point to that open circle? No. So what do you think that means about my absolute min? So we have a place we can say, oh, yep, that's the lowest we go, but it's open, so it doesn't count, so there is none. Local max. Okay, we know endpoints are out, so we're looking at any high point along our graph. So this one would be, but it's open, so does it count? No. Okay, this point. Right, is it higher than the points on both the left and the right? Yeah, I mean, it's not connected, but the definition doesn't say it has to be connected. So that would be f of 0 equals negative 1. Okay. Is this one higher than the points on both sides? No, it's higher than these, but not higher than those, so it wouldn't count. Keep going. What about this one? Local min. Lower than points on either side, but it cannot be an endpoint. So we know this one's out because it's an endpoint. Right, what about this point right here? We probably wouldn't think of it right away because it's not connected to the graph. But if I go to the left and the right, is it lower than the points on both sides? When I look to the left, the points are above it. When I look to the right, the points are above it. So it is still a local min. It doesn't have to be connected to the graph. Where else would we have a local min? X is -2 and y is -3. Okay, can an open circle count for anything? No, so that's out. This is also open, so it can't count. This is not going to count. It's lower than the points on this side, but not that side. So those are the only local mins. All right. Any questions on those? So that's what the first 4 questions on your homework. Just going to be looking at graphs telling me maxes and mins from those graphs. Let's see if we could draw a graph to meet some requirements. So we want to graph an absolute max at 5. Okay, so these are, I should have been a little more clear. When I say an absolute max at 5, I mean when x equals 5. Sorry about that. So when x is 5, that is my highest point on the graph. Now, I didn't tell you what the y value was, right? Because I just asked for a graph that made it work. An absolute min at x equals 2. So when x is 2, that is the lowest my graph hits. When x is 5, that is the highest. A local max at 3. What does that mean? Yeah, there's kind of a little peak. So we know at 2, that is the lowest it goes. But when I get to 3, I have to have some sort of little peak in my graph. So it's going to have to go up and then start coming back down. And local mins at 2 and 4. If 2 is also a local min, what does that mean? It's not an endpoint. So I have to have something to the left. So maybe my graph is just coming in like this. You could even give it a starting point. Maybe it just starts at 0, 0. Okay, if 4 is a local min, that means my graph has to come back down, kind of peak there, and then we're going to go back up. Can 5 be an endpoint? Yeah, because that was just an absolute max. Now, is this the only graph? No. Let's run back through our requirements and make sure we met them all. So, do we have a highest point when x is 5? Lowest point when x is 2? Local max at 3, local mins at 2 and 4. So the next couple things, we're talking about the extreme value theorem. And it says if you have a closed interval, so 2 endpoints, they're closed, so no open circles, then you have to have a max and a min in that interval. Right? Notice this is only for continuous and closed intervals. So if we have going to positive or negative infinity, that wouldn't be a closed interval. If we have breaks in the graph, that wouldn't be continuous. So if that's true, this is just some situations. If I'm going from A to B, we have endpoints, then I have to have an absolute max and absolute min. When we have an absolute max, my min would be one of my endpoints. Here we have the same absolute max, we hit it twice, and one absolute min. What would this be true if we had a break in our graph? Not necessarily. It could still be. but it's not guaranteed, because if we have breaks in our graphs, we might have like an open circle in the middle. And so then when I look, my absolute max is an open circle, so that wouldn't count. We have an absolute min still. Does this one have either? No. My first endpoint was open, so it didn't count, and this is going to positive infinity, so there's no max. So it only works on those situations where the function's continuous and we have two endpoints. So then the question is, how would I find those values? Think about what you know. How do we find maxes and mins? What's zero? The derivative is zero. So we're looking at places the derivative is zero. Those are where we get our local maxes and mins. And so then that's what the next slide tells us. If you have a local max or min, then the derivative is zero. It is possible to have a place where the derivative is zero, but we don't get a max or min. If we think about x cubed, we graphed it. Did it have any maxes or mins? No. But if we think about the derivative, when does that equal zero? At zero. So zero is a place where the derivative equals zero, but we didn't get a max or min. So when the derivative is zero, that's when we could have a max or min, but it's not a guaranteed thing. There are also situations where we could have a max or min and the derivative does not exist. Because remember, for the derivative to exist, you can't have corners, right? Because at a corner, we can't draw a single tangent line. So for instance, at an absolute value, this definitely has a lowest point, but the derivative is not zero there. The derivative does not exist. So when we're looking at things where the derivative, or where we could have a max or min, we have to consider where the derivative is zero or where it does not exist. And when we put those together, we get what are called critical points or critical numbers. So the last thing we're going to practice today is just starting to find some critical points, and then we'll continue that on Monday. So a critical number is just any x value where the derivative is zero or does not exist. And every max and min will happen at a critical number. So if we have those critical numbers, those will be the places where we can have a local max or min. So if we have to find maxes and mins, we need the critical numbers. Let's practice finding some critical numbers. That means we have to think back to all of our derivative stuff. Good news, no differentials, no related rates, no implicit differentiation. We're just doing basic derivatives again, okay? As this is written, what would you have to do in order to do the derivative? Product rule. Would it be easier to multiply it out first? Probably. If I just multiplied those, I would have 4x to the 3/5 minus, okay, this is an x to the first, that's like 5 over 5. So that would be x to the 8 over 5. So now let's do our derivative. So exponent comes down. Subtract 1 from the power, so 3 over 5 minus 5 over 5 would be negative 2/5. Minus, this is 8/5 x. If you subtract 1, so minus 5 over 5, you get 3/5. So we need to find critical numbers anywhere this is 0 or undefined. Okay. Different options for doing that. What does a negative exponent mean? So if I set this equal to 0, what would you do? So we would have 40x, 2/5 plus 3/5 is just 1, equals 60. Divide by 40, so we get 3/2. So my critical points. 3/2 is where this derivative is 0. Is there any number that would make this derivative undefined? If you look back here, undefined, think about, is there any number you couldn't plug in for x right here? 0, because it's on the bottom. So when I look at this one, that tells me, oh, x can't be 0 because the bottom of my fraction would be 0. So the derivative is undefined there. So that's my second critical point. Let's do, so those are the places that could be maxes or mins. To actually find them, we'll talk more about finding out if it's a local max or min later on. In this section, we're just going to be focused on finding critical points and determining the absolute max and min. So absolute max and mins could happen at endpoints, and they could be in the middle of our graph. So basically, if we have an interval, once we get our critical points, we are going to plug the endpoints and the critical points back into the original function to get their y values. Then the highest y value would be our max, and the lowest y value would be our min. That's our absolute max and min. We can't tell locals just by looking at that, so we're going to have a little more to do the locals, and we'll do that later. But let's see if we can do an example and find the absolute max and min. All right, first of all, for this theory to work, we have to have a closed interval, and it has to be a continuous function. Otherwise, we can't use that. This is a polynomial, so it's continuous. We have a closed interval, so we're good. So we need to find our critical points. So that's when we do our derivative. So we get 3x squared minus 6x. And then what do I do to my derivative? What could you take out of that? I'm going to go ahead and pull out a 3x. So we get x equals 0 and 2. Those are my critical points, or my critical numbers. Is there anywhere where this derivative would have been undefined? No, we didn't get a fraction, so we don't have to worry about that. So then, to find our absolute max and min, we have to test our endpoints and our critical points. Okay, so my critical points are 0 and 2. I should mention, if you have a critical point, let's say we had gotten -3 as a critical point. Would it be relevant here? -3. My interval says I'm only looking between -1/2 and 4. So if you get a critical point that's not in that interval, you don't test it. So now we're just plugging these back into the original function to see what we get. So if I put in a -1/2, so -1/2 to the third, 1/8 minus 3/4 plus 1. So 1/8. You put in a 0. You get 0 minus 0 plus 1, which is 1. We put in 2. You get 8 minus 12 plus 1, which is -3. If we put in a 4, 64 minus 48 plus 1, and that gives us 17. So what's my absolute max? And my absolute min? We're looking at the highest and lowest y values. Mm-hmm. I'm going to skip for a minute. Let's go to example 6. So if I want my maximum and minimum values, what would you probably do first? Distribute. So let's see, if I distribute 30 divided by 5 is 6 times 3 is 18x minus 3/5 x squared. So the derivative of 18x is 18 minus, the 2 would come down, so we would have a 6/5 x. Set that equal to 0. So you can multiply by 5 over 6. 18 divided by 6 is 3 times 5 is 15. So x equals 15. What do we call that point? That is our critical point. Okay, so to find the maxes and mins, we have to test both endpoints and our critical point. So if we put in 0, we get out 0. If I put in 15, 3/5 times 15, 30 minus 15 is 15. So 9 times 15 equal to 35. What happens when you put in 30? Because you get 3/5 times 30 times 0. So what does that mean? Technically, as long as they're the same, you could have more than one. So we could say both of these count as the absolute min because they're both the lowest. And then this is our absolute max. What questions do you guys have for me so far? Okay. I think I'm going to go ahead and stop here for today. So Monday we'll just practice more of these. Your assignment we're going to do page 280, 3 through 6, 31 and 37. On problems 31 and 37, make sure you read your directions. You are doing the critical numbers only. You don't have to find maxes and mins yet. Okay, so the first 4, 3 through 6, you're just looking at a graph telling me where the maxes and mins are on the graph. 31, 37, you're just finding critical numbers.